Yes, sir. Joined. Yes, sir.
Yeah, okay. So today, good evening. Today we will be discussing the bearing surface in total hip arthroplasty. And that's a hot topic for either is it for DNB, for MS, for D-Orth, and it's a very, very hot topic. So I will go into the details one by one. So you understand and you should be able to write and do a justification of the bearing surface in total hip arthroplasty. So, CHARNLEY worked very hard for the hip arthroplasty, and first final hip arthroplasty design came with a PTFE, and that is the polytetrafluoroethylene was the material which was used on the estabular side, and the fifth and the final design which was finally introduced in 1960. Estabular component was PTFE, and the cemented component, femoral component, was the stainless steel as what you see here. That's a 22 millimeter head, and that's a femoral first generation stem, and this was PTFE. At that time, the cement was not there at that time. And CHARNLEY published in 1961, CHARNLEY published a very early result of he used to call LFA, that is called as low friction arthroplasty. And he came to the idea of low friction because of 22 millimeter head. And he published the initial results. And implant fabrication at that time, he used to do himself, or there was a workshop in Wrightington Hospital, and this was a lathe machine and whatever he was, that one machine or two machines were there at his residence in his garage, and he used to prepare himself, he used to fabricate himself estabular cups, and the femoral stem was fabricated outside. And he did a lot of hard work during this innovation. And the joint articulation, that's a polytetrafluoroethylene. The joint articulation was successful in first 2 years after surgery. More than 90% of the patients were revised within 2 to 3 years of implantation because there was severe wear and inflammatory response provoked by this PTFE. And he did not realize at that time. And the wear material property were not tested during that time. And first time he came on a British platform and said to all his colleagues that I have found a material which is going to be in the body for more than 50 or 100 years, and people should start using it during his first meeting. He had the courage to come back in 1961 or 62, stating that please do not use this material. I did not realize his wear property, and when we opened all the hips, they were looking like infected hips. This is like a granuloma because of the reaction of PTFE. So he was fairly depressed. So, and he called every patient, and it was UK to call patient back was very easy because it's a small country and a close contacts. So he could bring, I think he did about 231 hips at that time and he literally called 90% of hips back, and he tried to revise, try to take out the implant and get into excision arthroplasty.
Hello, sir.
You stop operating almost a year or two. And the concept of selecting PTFE was it was a low friction without considering its wear property, and that was one of the disaster. That was a great mistake that CHARNLEY did at that time with polytetrafluoroethylene. This is a plastic material. Then in May 1962, a salesman, that is his name was Binz. He was from Germany. He came to Wrightington Hospital for something else, and he met Mr. Krevin. Harry Krevin was the bioengineer of John CHARNLEY. So he just he came and saw him, and he just showed the material. That is ultramolecular polyethylene. He showed this material, and then once he saw that, then he called CHARNLEY, and the CHARNLEY saw the material. When he shown the material, CHARNLEY just put a thumb in that material, nail, and he walked out telling the Krevin, you are wasting his time and wasting everybody's time. And this was reported by Wog. Wog was the one who did high table osteotomy actually. He was his associate. Wog was his associate. So that was the time that CHARNLEY did not like this material. And CHARNLEY went on a 3 weeks trip to Copenhagen at that time. But he was away for 3 weeks. But still, Krevin thought that we should do something on this material, and the Krevin decided to test this high ultramolecular polyethylene on a wear testing machine. This is the first wear testing machine in the world. This was in Wrightington Hospital. The wear machine was. It was very primitive at that time. And when CHARNLEY returned after 3 weeks back, 3 weeks in June, Krevin showed that 3 weeks wear data. And after running a day and night for 3 weeks, the new material had not worn as the PTFE, and would be worn in 24 hours as the PTFE. And the 3 weeks, there was no wear at this material under the same condition. So he showed the wear data to CHARNLEY. Then what he said, there is no doubt about it, we are on. So that is the way in 1962, the ultra high molecular weight polyethylene came into picture, and then CHARNLEY started working on this material. So this ultra high molecular polyethylene is a unique polymer with outstanding physical and mechanical both properties, physical as well as mechanical properties. It is chemically inert. It did not produce. What it did then, you will be surprised to hear this. So he didn't want to take a chance. So what it did, this ultramolecular HDP material, he made it powder and put his own thigh. He opened his thigh, small 2 centimeter, and opened it and put this material inside under the fascial lata. And after a couple of weeks, he took out that material again and saw there was no reaction of this. So look at the man, what a daring of this person, what involvement of this person was. He did not put it into animal, he put it in his own body. So that was a case. So he thought it is a chemically inert material. Then lubricity is very good, lubricity. The impact resistance was very high, and abrasive resistance was very high, because hip has a lot of adhesive wear actually, not abrasive wear. But that time he didn't realize actually what was abrasive and adhesive wear, and that's why he did a lot of work on lubrication actually. There's a great pioneer work of lubrication of John CHARNLEY. So he thought also abrasive resistance wear. So this material was giving you all possible thing which can be into the artificial joint. So how this material is prepared? So UHMWPE, that is ultra high molecular weight polyethylene. So is it is actually polymerized from ethylene gas. So it is converted into powder form first. These are powder, and then it can be processed. It can be processed into the bars or sheets. Our powder can be consolidated into sheets, or you can also convert into near net shape of the implant. Then you can finalize this. So this can be put on the final implant, then it is machined, and then get the final shape inside. So there are 2 or 3 ways this material can be used, from the powder to a sheet, and also direct implant manufacturing can be done. That's called as a compression molding, which I'll tell you what is the importance of this compression molding. So by and large, for exam, how this material is prepared is from the ethylene glass powder into sheet or sheets or into the direct implants. That's the way it is manufactured. So process of compression mold. The direct compression implant from the resin powder is possible. Either some of the material are directly done, or it can be converted into sheets, and then implant can be machined from the rods or sheet. Depends. So that's called as a ram extrusion. And this process, this manufacturing process, the sheets are prepared on hot isostatic pressing. That's called HIP, hipping. And the material is brought very close. The molecules are very broad. This all powder form is brought very close. So there are no defects in this material which can lead to crack propagation or fracture. So it's very important, called as hot isostatic pressing is done with this powder. So the compression mold also, sometimes in the knee and the hip also, both can be done as a compression mold. Powder can be put and individual implant can be manufactured, individual implant. But that's a very laborious procedure of individual implant, because it is just not possible to do a bulk manufacturing with this compression mold implant. So what is the advantage of compression mold implant? There are no white bands, no delamination, wear is very low. Clinically, it has been worked out at 25 years by Merrill Ritter, a compression mold. He was the only person who was still working on the compression mold implants in the knee as well as for the hips. So his statement was Merrill Ritter, and I attended that meeting, one of the meeting with Merrill Ritter. Why try something which is not clinically long term? So he was very fond of using the compression mold. Unfortunately, the company has stopped manufacturing in 1994 because it's just not possible to provide millions of implants across the world with just a compression, just individual compression molding implants. So this is not manufactured now anymore. But we have a different technology at this. So this is the first paper came out. It is a very mind-blowing paper between Dr. Ranawat, this is Ranawat and his two sons, and this is Merrill Ritter. So this is the first study. They did a work of the same implant, but the acetabulum was different. So 162 compression molded implants were done by Merrill Ritter, and 72 acetabulum were done by machine, which was machine-made acetabulum was done by Chitranawat. And they came to conclusion, compression mold, the wear rate was 0.5 and machine was much more higher and p-value was significant. So this was the first paper showing that compression mold has wear rate is extremely low compared to machine made. So then these convention poly, the wear rate was getting higher with normal machine made. So people thought, Bill Harris from Mass General Hospital thought we should do something. And he came out with the idea of formation of cross-linking. So today we are using a highly cross-linked poly. How it is manufactured? This is the carbon atom with 4 hydrogen. And when we want to do a cross-linking with either chemical or radiation, so what happens actually? This bond is taken off. That 2H are taken off, and we have a cross-linking from carbon to carbon. This is a cross-linking which you developed after the radiation. And these free H radicals are taken off. They are taken off. So again, this is the carbon with a 4 hydrogen. And when we want to do cross-linking, we will just take out this area, and we will have a cross-link and have a cross-linking bar with gamma radiation or sometimes with the chemical radiation. So that is the way we will do a cross-linking, so this material becomes much better and the wear resistance is extremely high. So this was highly cross-linked poly, and the proof was in the hip stimulator, and there was a great experience of 3 mind-blowing papers in the human, and all these 3 papers showed that cross-linking helps to reduce the wear rate. And one of the paper, again, this was from WROBLEWSKI. That is, WROBLEWSKI is the next successor of John CHARNLEY. He's still alive. So high level of cross-linking, however, extremely high level of cross-linking will result in material failure and it becomes brittle. So our radiation has to be within the limit. Irradiation of polyethylene with a gamma dose over 100 megarad will reduce the mechanical strength. So we don't do much more than between 5 and 7.5 megarad is cross-linking. That is the value we use for cross-linking this polyethylene material. So then how to sterilize this material once it is all manufactured in the factory. So we used to this material we used to do in the air permeable packing at that time. So this material will have to stored in air permeable packing and a gamma sterilized in the air. So gamma sterilization we were done on the air, and we didn't do it in the laminar, and we didn't do in the other type of nitrogen free atmosphere. And then because of the air was trapped in this material, after keeping in the shelf life, it started getting oxidation. It goes in, undergoes into oxidation degeneration. And this material, when you after 2 to 3 years, it becomes so brittle, it gets fractured, and the wear rate was very high. So this was, we were not knowing. So it was, the packing was done in the air with a gamma radiation, and a simple packing where still the air could get inside. So we realized that there is oxidation taking place because oxygen was going inside, and this particle used to get degradation. So we started using what is called barrier packing. Barrier packing goal is to minimize oxidation. So today we have a double special packing. We have aluminum foil. We have so much thing, and now we use this either into laminar flow air atmosphere, or nitrogen free special cubicle is made, so that we are packing with this material, so that the oxygen does not go inside the packing. So oxidation degeneration leads to increased crystallinity, increased density, loss of mechanical property, and increased brittleness, which I just now told you. So we don't want any oxygen particles at the time of packing. Otherwise, it will start degradation. So the other possibility was, instead of that, ethylene oxide gas sterilizer. This can be also used. So a lot of companies do on ethylene gas sterilization. Does not influence the physical, chemical, and mechanical properties of this material. After sterilization, there is a residual ATO which allows to diffuse out to reduce the adverse. So you can't use today, it is packed, tomorrow you can't use it. So you allow them to keep it in the shelf life for at least for a couple of weeks before it gets diffused, the ethylene gas oxide. So it is another way, either it's you do it under this, or you do it under ethylene gas sterilization. So the wear is defined, the loss of material from surface as a result of motion between these surfaces, and the material is lost in the form of particle debris, and that is the biggest problem. So we have adhesive wear. It is very important exam. Sometimes they ask the examiners, the hip has got adhesive wear and the knee has got abrasive and fatigue. So we are going to talk today only on mainly adhesive wear of the adhesive wear, which is very, very fine particles are taken. And these fine particles are nanoparticles. And they produce a lot of problems which will come to in osteolysis. But abrasive wear in TKR, the particles are large. They are not taken by the phagocytes. So nanoparticles are taken by the phagocytes, and TKR fragments are not taken by the phagocytes. That's why we didn't see a lot of osteolysis in the knee, and we only saw in the hip. So the wear rate in the cemented hip is on the lower side, and then the uncemented hip. So there is no question the wear rate in the cemented is low than the is much more in the higher in the uncemented. But today, with a new material, which will come to that, with the ultra-high molecular, the wear rate has come to, whether it's cemented or uncemented, does not matter. So how do we measure this wear? This is our own patients' examples. So how do we measure the wear? So in olden time, this is a radio marker in the acetabular cup on the back side of the acetabular cup. There's a radio marker, and this is a femoral head. So we know what is the size of the femoral head, that is 22.2.5 millimeter. And this is the distance we measure from here to here. On a computer analysis, we measured this distance from here to here. It was in a small cup, it was about 6 to 7 millimeter. In a larger cup, it was about 9 to 10 millimeter. That was the thickness of the poly. So this was the thickness of the poly. You see, it is a beautifully uniform. See, after 22 years, now there is a wear which has taken place, and it is almost touching the radio marker. And that's the same. You can see that's an original acetabulum, and this is a taken out acetabulum. You can see the light through completely. So it is almost one area. It is already, the poly has been broken. So we have some formula, which is formula to measure this wear on the plain X-ray. It is formula, and this formula was devised by one of the fellows from Wrightington Hospital, Dr. Pradhan, who worked at KM Hospital when he was a houseman, registrar, or MS. So he's got a big name on this Pradhan's formula of measuring wear rate. So, but one of the things which is the easiest way for all of you, rather than going into mathematical, it's very easy to do this measurements, because we know the femoral head size. Then you can calculate according to the magnification. This is the way the wear takes place. So what happens to these particles? You realize the particles that these nanoparticles are taken by the phagocytes. Then they convert into macrophages. Then they start releasing cytokinins, which are destructive. That is like alpha tumor necrosis or interleukin 1, interleukin 6. These are the three major cytokinins which are very destructive to the bone. Start osteoclastic activity. So that is the even sometimes they have a major giant cells in this pathology. So basically, phagocytes convert into macrophages. Macrophages start giant cells, convert into giant cell. They start releasing cytokinins. Cytokinins are nothing but alpha tumor necrosis, interleukin 1, interleukin 6, and they are known as pre-osteoclastic. They start a resorption of the AT, totally cemented, trochanteric. And you see after 17 years, because of the little bit of wear here, you see the osteolysis. This is a massive osteolysis. Whole ischium is washed out. The whole cup has gone inside. So that is known as osteolysis. Sometimes we see such a massive osteolysis. And this was a unique disease, human, we have created and not the nature has created. So we need to find out a solution for this. Okay. So
yes,
this polywear, there's no question. There are three important papers stating that there is a polywear and the biological reaction. If the polywear does not take place, the biological reaction does not come, because the load of the poly does not come on the tissues. So these are three important papers: Kabawashi, Porter, Maloney. The wear correlates with development of osteolysis. More the wear, more with the osteolysis. So we have come to conclusion. There is no question. So it was cemented also. And what about uncemented? We thought uncemented we will not get the osteolysis, but we see much more osteolysis in uncemented hips. And these are one of the example. This is the total hip. It looks very benign, but the patient had some symptoms, some discomfort. So we did a CT scan of these patients and look at this. These are osteolytic area. Almost there is a break here on the acetabular side, on the medial side, and these are osteolysis. This is on the back side of the acetabulum, and it is reported asymptomatic osteolysis, silent osteolysis is almost 48%. Why this happens? So we did not realize, even though there was no major wear is this, but there was a backside wear. When you put the liner inside, there is a locking mechanism. This locking mechanism is never 100% right. There is always micromotion take place. And due to this micromotion, there is a particles which are thrown inside are very much nano. more than the articular surface particles. And these particles are making havoc. So we do see a lot of osteolysis in the uncemented hip arthroplasty because of the back side of the wear. So today we have come to the new locking mechanism. We are trying to get the best locking mechanism, and new poly, that is cross-link poly, has reduced osteolysis, which will come to 1 or 2 papers. So there is silent osteolysis. Any patient after 7 years or 8 years complains of some discomfort. X-ray looks fine. Get a CT scan. That is that is important message I'm passing to. So these are my own patients. This is a post-op. This is a radio marker here on uncemented hip, and we do measure the distance. And after 12 years, you see the distance has reduced almost about 3 or 4 or 5 millimeter. And this is the poly which I took it out, and the new poly again put, and then that's a new poly, and this is the poly which is taken out. So on a cemented side, this is the last paper today in the literature of 50 or more than 30 years follow-up of one institute, that is from Wrightington, WROBLEWSKI. The follow-up has more than 42 years, and looking at the data, 93% at 10 years, and today 50% only at 30 years. 50% of the hips have already failed at the 30 years. So they are all gone. 50% have gone on revision. That's the data of last cemented data coming from the original institute. Anybody knows WROBLEWSKI?
Yes, sir.
Yes, sir.
Yeah. Yes. So this is he was the next successor of John CHARNLEY, and this man was born in India and studied in India near Panjgani, and he was a Polish. This one, his father was working in the British military, so he came and visited his birthplace. And today there are some few people are still near Panjgani and near Kolhapur, and the Polish people are still living there. And he just came and met them. So that was WROBLEWSKI. And he also came to deliver a very important lecture of Dr. Dholakia way back about 8 or 10 years back in Mumbai. Anyhow, WROBLEWSKI finally wrote in his book, last page, 2 major factors will decide the ultimate fate of arthroplasty. One is wear, and second is effect of implant on the function of the skeleton. So what is happening to the bone actually? How much stresses are going through? How much remodeling is taking place? And these two are going to give an idea of ultimate fate of the arthroplasty. So the highly cross-linked poly was also a baby of WROBLEWSKI, but this he had a very small number of patients at that time. So he had only a highly cross-linked poly, which was a chemical cross-linked poly. He only had studied 11 patients, 15 years follow-up. Initial wear first was very low, and the wear after that there was no progression of the wear. So what he did on one side was a normal totelet, and the other side was the cross-linked poly we used. And this was 18 years follow-up of his own patient. You see the wear has taken place. Wear has taken here on the normal side, where the normal polythene was used, and a cross-linked poly was used. There was no wear. So this made him to understand there is a possibility of getting into the cross-linked poly. So that was the data available at that time. It was very small data. But the great breakthrough happened due to Mass General Hospital, MGH, USA, and this is William Harris. I don't know whether he's still alive, but I had the opportunity to meet him in 1998 or 99. Attended some lecture, a few other things. So he is the man who started working on a cross-linked poly. There is the largest stimulator lab today in USA at his Mass General Hospital. And after he retired, he handed over to his lab to Harry Rubash. And he's still working, Harry Rubash is still working on a highly cross poly and other areas. And we also had a great opportunity to meet this gentleman here in Ahmedabad. and as well as I met him many occasion as a very great surgeon and originator of cross-linked poly. I'm just give me half a second. Hello. I'll call you and I'm in a webinar. And lecture. Okay. Sorry. So, does reduced HDB wear on the lower osteolysis? Yes. There was enough data, and this is one of the very good paper from Young group, Gerald Young and his son. The incidence of osteolysis was 22% versus 0% for crosslink. Survivor at 10 was 97% on this side plus minus, and this was 100% with crosslink. So the mean wear rate was just 0.4 today with the crosslink poly. So there is no question the crosslink has come to our rescue. And some of the follow-up of 13 years follow-up of compare between conventional and crosslink poly, large data of 160 hips, younger patients, wear rate with conventional was much more, 0.1, and crosslink poly was 0.34, which also was there 0.4. So it is the wear rate has completely come down. Only thing which has reported recently was if you use too thin poly and a crosslink poly, you can get a small breakage here on the corners here with highly crosslink poly. So you have to be very careful. Minimum, what recommendation is minimum 4 to 5 millimeter poly should be there. You should not be less than that. A lot of people thought it was you can use even 3.5 millimeter and use a larger head to reduce the dislocation. But today we don't use now. We don't go now beyond 36 millimeter head. Initially we used 40 millimeter, but we are not now anymore using because you can get a breakage. So there are few report cases of crosslink poly. So that's
sir,
about. Oh yes.
Sir, sorry to interrupt. The meeting is going to be discontinued within 1 minute due to time limit. Just I'm going to start in 5 minutes. Again, I'm going to send you the invitation.
Okay, then we'll start with ceramic. Okay, done.
Yeah, we'll start with ceramic and metal. Okay, sure, sir. Sure.
Okay,
Sure.
okay.
Okay.